Okay, so for the general goal of the project, the original idea we had was just the basic sun follower that many people in this class have done apparently, but we came up with this idea on our own before we really had any idea that that was a common project. So what we said was we wanted it to have a solar panel that will find the area of highest solar intensity. So that way a solar panel in a solar farm or just simply someone backpacking out on the field of in the trails and they need to charge their phone. We were more thinking like large scale, but to correct the solar panel to be fit to the sun in the best possible way. That was the general idea of the project. And we started off by making a high-level block diagram, which I will pass off to James.
All right. So for milestone 1, which is this milestone, we have the sun, or in this case, a flashlight, which is sending light to 2 different photoresistors. And the idea is that these photoresistors will tell the solar panel, or in this case, just send a signal to LEDs, saying whether or not the solar panel needs to move up or down, and how fast it needs to do that, like how much it needs to move. So we do that by taking a variable resistance from those photoresistors, converting that into a voltage with a voltage divider, using op-amp math to calculate how much, like in which direction it needs to move and how much it needs to move. And then we send that to the LEDs, which will actually vary their intensity based on how much it needs to move. So for the op-amp math, we first have an inverter, or an inverting amplifier that just kind of inverts 1 to 1 to get one of our voltages to be negative. And then we also have a inverting summing amplifier, which is doing 3 things. Number 1, it's converting that negative back into positive. Number 2, it's then subtracting that voltage from the other voltage. So that would be like we're subtracting how much it needs to move up. We're subtracting how much it needs to move down from how much it needs to move up. So we have like a single variable. And then it's also amplifying that by a factor of, I think a factor of 10, so that we have a better signal to send to our LEDs, or eventually what will be sent to the motors.
Okay. And the next big thing we needed to cover was a functional circuit simulation. So, okay, regarding our circuit simulation, we have these. These were actually parallel resistors that we combined over here, or not there, over here. These 2 pull-down resistors, those were actually parallel resistors to get more accurate resistances. So we combined 2 resistors to get a more accurate value, just to use that proof of concept. This R22 and R20, these are to simulate just photoresistors, because you can't really use a potentiometer in LT Spice. From there, we have this inverter that we invert the signal of 1 photoresistor, so that way when we go to a summer, it's actually subtracting.
Yeah, so this is specifically a non-inverting, this is specifically an inverting amplifier, but it's inverting it to 1 times what it already is.
Yeah.
So essentially just inverting the value.
So yeah, it's basically 1 plus negative the other. And when we get to this this addition, also known as subtraction, operation that we perform here,
it's adding of a negative number.
Yes, that is a 10K ohm resistor, because we need to amplify the voltage in order for our LEDs to work in the physical circuit. And we use some comparators to set a threshold, basically like a low-pass filter, to say if it's less than 0.5 or if it's greater than 0.5, but in between those numbers and 0, to not do anything, because we don't want the stepper motors in our solar panel to actually just go back and forth when they're not at a perfect equilibrium. And then we have some LEDs and motor outs that that James can probably explain.
All right,
better than me.
So there's two different sections of this. The bottom section is probably the most important. So this will be, this signal here is either going to be positive voltage or negative voltage, depending on whether this subtraction resulted in a positive or negative number. So if this was a positive number, then that will mean that there is more light on the top of the solar panel than the bottom of the solar panel. So that means it needs to be angled up to better angle itself to the sun. So that will light up the top resistor to say, hey, you need to move up. And then the same thing for the bottom. If it's a negative voltage, we have an LED going backwards instead to say we need to go down. And then this signal will also go to our motors in future milestones. Up here, we have another signal which will tell us essentially when it's okay to shut off the motors because we're not using it, because the voltage difference is too small to matter.
Mm-hmm.
So if it is less than half a volt, there's no point in really moving up. And if it's more than negative half a volt, so like closer to zero than that, then there's no need to move down. So these will also activate if it needs to go the other way. So we don't need to move down and up at the same time.
Yep, perfect. So here, I'll just quickly run this simulation. And just to show, we have a sample 20K resistor and a sample 15K. And when we hit run, the values are what we expect them to be. So the photoresistor in the bottom is around half a volt. The photoresistor in the top is a little bit less than that. And then performing this operation and going through all the different steps will then lead us to have a basically zero, or it should be zero voltage for the down equilibrium and 9 volts for up equilibrium. So that is telling the motor to move up, which is exactly what we wanted to do here based on these two resistor values. And if we change it, you'll see similar results.
Oh no, it needs to move. It needs to move down. It doesn't need to move up because the resistance is higher.
Yes. Yeah. Sorry.
The resistance is higher on the top, meaning there's more light on the bottom. So it does not need to move up. It actually needs to move down.
It needs to move down, and it'll do that.
And you'll see that here. So go to motor up down in the simulation.
Yep.
For
motor up down, it's negative.
Yeah, which means again it needs to move down by not that much, but by a little bit.
Yep. Okay. So moving on from the circuit simulation, now it's time to show the actual circuit. So right in front of us here, we have.
Is this the right way around on the camera?
Yeah. So right here we have everything that we need.
So here's my sun here. So if the sun is more shining on this part of it, which I think is that showing up as down?
You can't really see. You can't really see. Here, I got it.
Okay.
So you can see the green LEDs. Sorry, you can't really see the green LEDs. There's two different LEDs here, and you can see that they light up based on where it needs to move.
And even if I have a light that is covering both of them, so a brighter light like another light like this, even if it's covering both of them, whichever one is covering more, the LED will light up here respectively.
Yeah, this LED is lit, and that LED
if I'm exactly between them, they're both getting light right now, but both LEDs are off because they're getting the same amount of light.
Okay.
And then if I adjust it slightly, it'll pick which one it wants to do, which way it needs to go. And there's also like a variation where if it's like only a little bit more light on one than the other, then you can see here that the LEDs will only light up slightly.
And so you can see we have several 9-volt batteries just throughout because we needed several 9-volt and negative 9-volt grounds, or negative 9-volt rails. We had a common ground terminal throughout 2 different boards. We have our voltage divider, photoresistors, the subtracting op amp, or the summer technically, and the inverter are all taking place right here. The LEDs are then connected to the output of said operation just to test if those signals are right before we send them to the comparator. And then Sean could tell you all about what happened over here because it's on a separate board for a reason.
Yeah. So this yellow wire is taking the value out of the photoresistor portion of the circuit and putting it into the comparator op amps. So this second breadboard is taking a 0.5 volt reference voltage for two comparators, and then using the voltage coming from the photoresistor circuit, we're comparing to the 0.5 volts, and then if we're higher or lower than that, we turn on a green LED or a red LED and that's right now kind of simulating if we were going to be driving the stepper motors to go up or down. So we had a little bit of trouble with this. Originally, we were having some overcurrent problems when we were having a negative voltage go into the op amp. So like our waveforms from the analog discovery would shut off, talking about overcurrent.
Which was immediately a red flag because an ideal op amp draws zero current.
Yeah, so we kind of remedied that by putting a resistor in line with the voltage coming from the photoresistor circuit. So that got us below the current that it was upset about. But it's still a little finicky having the threshold be correct. So right now it's pulling the voltage to the correct side, to the correct LED. So it'd be moving the motor in the right direction. But the threshold, like low pass filter kind of idea there, that would make the motor not move if the lights are, or if the photoresistors are getting an even amount of light, is not working.
Should I demonstrate that?
Yeah.
All right. So yeah, the idea behind this is if there's no light, then it doesn't need to move in either direction, and they're both on. And then if there's light on one, then it should say we don't. So this is light going on the top, and that says we don't need to move down. And then if there's light on the bottom, then it will say we don't need to move up. So when there's no light, it's supposed to say we don't need to move up or down. Although this isn't working, likely because, again, because of the finicky nature of the op amp.
Yeah, what we want to be seeing here is for both lights to be on or off when the light is evenly distributed. Right now, that threshold just isn't really working. We think somewhat to do with the op amp being non-ideal. So we have to look a little bit more into that because we haven't learned too much about that in the lecture yet.
Okay, so we pretty in-depth went into the problems we had with this comparative op amp. But when it comes to just general design choices that we made that are beyond just that basic intro to ECSE stuff, where we're just doing basic op amp stuff, basic resistor stuff, we were using some advanced concepts like a common ground throughout several breadboards.
Yeah, across both the analog discovery and both of the boards themselves.
Yes, we were using several boards. At one point, we even had multiple analog discoveries just for bug testing. We had like 3 or 4 9-volt batteries for different 9-volt and negative 9-volt supplies.
Yeah, that's another thing. You don't use negative 9 volts or put the battery backwards in intro to ECSE,
Yeah.
So that's new.
Negative voltage was a big no-no before we got to this class. So these were all new design choices that we had to make. And the last thing that we wanted to touch on was just a question we had, which is...
Yeah, so really our big question that is still a little bit unsolved is really some of the non-ideal versus ideal op-amp stuff. Because obviously our simulation is giving us what we want, and then the real circuit is giving us some different trouble. So we're pretty curious about how to go about dealing with unideal op amps and the right problem solving skills there. So I think that's kind of the largest unanswered question for me, at least.
And what's also interesting is it started to work better when we gave it a negative voltage into the op amp, which shouldn't be the case. It should just work either way, because we're not supposed to be outputting a negative voltage. So right now it's like not what we that's why right now it's not working exactly how we want it, but it was surprisingly an improvement when we added that negative voltage.
Yes. And just to wrap it all up, just going forward, you can see from our LT Spice diagram, we have signals from motor outs because we want to actually send this voltage out to a stepper motor. We want it to actually move a solar panel. We want to actually generate power. We have many things that we need to do going forward, especially if we were to look at our just general milestones. We want to actually move the solar panel. We want to actually generate power and make it clean, and maybe even send it out to like a phone or something if we can do that. We have lots of ideas on what we can do with this sun follower, and hopefully get it working in the future. And cover everything.
I think so.
All right.
Thank you.
Thank you.